Rational, irrational, and real numbers. Just as subtraction led us to zero and negative numbers, and division led us to fractions, finding the root leads us to irrational numbers, and irrational numbers complete the set of real numbers. Real numbers are the numbers that exist on the number line. Irrational numbers are real numbers that cannot be expressed as a ratio of two integers. In decimal form, they extend forever and never repeat. And there are an infinite number of irrational numbers between any two integers. So for example, if I had 1 and 2, well, I know that the square root of 2 falls in between here, as well as the square root of 3. And you could put those over fractions, like you could do the square root of 2 divided by 2, and that would be closer to 1. And then you realize that you can multiply your irrational numbers. For example, I'll do another one, the square root of 5, by any other number. For example, an integer. If you multiply 2 times the square root of 5, that's still irrational. Similarly, if you did 1 plus the square root of 5, that's also going to still be an irrational number. Now the square root of 9, that's considered rational, and that's because the radicand, or the number that's under the radical, 9 that is in this example, is a perfect square, because 3 squared is equal to 9. Now if the radicand is not a perfect square, then the root is said to be irrational. For example, the square root of 12. On the last slide, I explained the square root of 2. That's irrational. So is the square root of 3 and the square root of 5. As long as the radicand is not a perfect square, then the root is irrational. Irrational numbers were first discovered by Hippasus about 2,500 years ago. He was a Pythagorean, and the discovery was considered a problem since Pythagoreans believed that all was number, by which they meant the natural numbers, 1, 2, 3, and so on, and their ratios. Hippasus was trying to find the length of a diagonal of a square with sides of length 1. Instead, he proved that the answer was not a natural or a rational number. For a while, this discovery was suppressed since it violated the beliefs of the Pythagorean school. But Hippasus had proven that the square root of 2 is indeed an irrational number. An infinite amount of irrational numbers emerges from trying to find the root of a rational number. Hippasus proved that the square root of 2 is indeed irrational, since its value in decimal form goes on forever without repeating. Some of its digits are shown on the next slide. Here are the first 1,000 digits, but you can find the first 10 million digits on the internet. The numbers go on forever and never repeat in a pattern. So here's what the square root of 2 looks like to 1,000 digits. Soon thereafter, it was proven that many numbers have irrational roots. Other examples that were brought up are the square root of 3 and the square root of 5. And we know that the roots of most numbers are irrational, and these are called algebraic irrational numbers. In fact, there are many more irrational numbers than rational numbers, because you could put a square root around any two numbers, such as 10 and 17, and then square root that, and it becomes irrational. Now, some of you may be thinking of longer decimals. Well, if a decimal number has a pattern that repeats, it is considered to be a rational number. Irrational numbers never repeat a pattern, and sometimes you have to go out a pretty long way to see the pattern for a rational number that repeats, but it will. For example, 1/7 is equal to 0.142857, 142,857, 142,857, 142,857, and so on. It repeats forever, but can be written as 0.142857 with a bar over top of it. And this is representing the pattern that repeats forever. That means it is a rational number. And the square root of 2 has been calculated to millions of digits and never repeats. Since you can't write out all the digits of the square root of 2 or use a bar to indicate a pattern, the simplest way to write that number is the square root of 2. But when solving for the square root of 2, when you have x squared is equal to 2, and then you square root both sides to undo the square, there are two answers, positive square root of 2 or negative square root of 2. And these are in two different places on the number line. In order to avoid confusion, it was agreed that the positive value would be called the principal root and would be written as just the square root of 2, meaning you don't have to have the positive sign in front of it. The negative value would be written as negative square root of 2. There are an infinite number of irrational numbers. Here are just a few of them that fall between negative 10 and positive 10. You have the negative square root of 95, negative square root of 80, which is really close to negative 9 because the negative square root of 81 is negative 9. We have negative 6/10 times the square root of 85. We have negative square root of 8, negative square root of 2, positive square root of 2. You have negative square root of 2 divided by 10. You have the square root of 8, square root of 50, and the square root of 95. The other set of irrational numbers are the transcendental numbers. These are also considered to be irrational. No matter how many decimals you look at, they never repeat. But these are not the result of solving a polynomial equation with rational coefficients, so they are not due to an inverse operation. Some of these numbers are real and some are complex. But this year we are only going to be working with the real transcendental numbers. Pi is an example of a transcendental number, and it's the ratio of a circle's circumference to its diameter, and it's represented by the Greek letter pi. If we look at the simulation that appears here, we start off with 4 circles that have the same diameter, and we take that same circle and we are unrolling it to show how long its circumference is, or the circumference of one of them is. Notice if we start at 0, we end up rolling it out, and when it's done rolling out, it ends up falling a little past 3. So discuss why this approximation, 3 14/100ths, is an approximation and it's not the full value of pi. And then answer the question, is this number rational or irrational? Take a moment to pause this video and think about it, and when you're done, unpause it. Now, pi is an irrational number because it has a decimal representation that never ends, and it never settles into a permanent pattern. If we were to continue to write out the decimal value of pi, we would have 3.14159265359, and it keeps going. And there are supercomputers that have found over 12 trillion digits of pi. And there's actually a website that if you put your birthday in with 2 digits for the month, 2 for the day, and 2 for the year, it will actually find your birthday in the decimal approximation of pi. So that's pretty cool. And pi is the most famous transcendental number. It's the ratio of the circumference to the diameter of a circle. And people have tried to find the value of that ratio for many millennia. Only in the mid-1800s was it proven that there is no rational solution or value for pi. And since pi is irrational, meaning its decimal digits never repeat, and it is not a solution to an equation, it's considered to be transcendental. Some of its digits are on the next page. So here we can see many of the digits of pi. There are many more transcendental numbers. Another famous one is e, which you will study in Algebra 2 as the base of natural logarithms. In the 1800s, George Cantor proved that there are as many transcendental numbers as real numbers, And there are more algebraic irrational numbers than there are rational numbers. The integers and rational numbers which we feel more comfortable with are like islands in a vast ocean of irrational numbers, because there are so many irrational numbers around those rational numbers or islands.